January 22, 1970, 13:15, Greenwich Mean Time. A Boeing 747-100 sits at Gate 23, London Heathrow Airport. The aircraft registration, N736PA, Pan American World Airways Flight 002 to New York, John F. Kennedy International Airport. Captain William Morrison completes his exterior inspection, walking beneath the massive wing. The 747 measures 231 feet 10 inches from nose to tail. Wingspan, 195 feet 8 inches. Height, 63 feet 5 inches to the top of the vertical stabilizer. The aircraft towers above everything else on the apron. 2 stories tall at the fuselage crown. The distinctive hump housing the upper deck cockpit and first-class lounge creates the 747's unmistakable profile. First Officer David Chen inspects the main landing gear, 16 wheels arranged in 4 four-wheel bogies. Each main gear assembly carries weight that would crush the landing gear of previous generation aircraft. Flight engineer Robert Hayes examines the 4 Pratt and Whitney JT 9D3A turbofan engines. Each engine produces 43,500 pounds of thrust. Each weighs over 8,000 pounds. The massive nacelles hang beneath wings that span nearly 200 feet. The flight engineer's domain. Inside the cockpit, Hayes settles at the flight engineer's station, a vertical panel covering the entire right side of the cockpit. His position faces sideways, perpendicular to the pilots. The panel displays every aircraft system. 4 columns of engine instruments, 1 for each JT-9D. Fuel quantity indicators showing capacity for 52,300 gallons. Hydraulic system pressures for 4 independent systems. Electrical generation from 4 engine-driven generators plus auxiliary power unit. The 747 requires a flight engineer. The system's complexity exceeds what 2 pilots can manage while flying the aircraft. Hayes monitors power plants, manages fuel distribution, coordinates system configurations, troubleshoots malfunctions. 3-person cockpit crew, standard for wide-body operations in 1970. Cockpit configuration. Morrison occupies the left seat, Chen, the right seat. Between them, the center console holds throttles for 4 engines, radio controls, and numerous system switches. The instrument panel extends across both pilot positions in familiar Boeing layout. But the scale is different. Everything larger, more redundant, more complex. Airspeed indicators, altimeters, attitude directors, heading indicators, all analog, all mechanical, all requiring constant cross-checking and monitoring. No flight management computer, no auto throttle in early 747-100s, no electronic engine control. Every system operates through mechanical, hydraulic, or pneumatic actuation with analog instrument feedback. Passenger loading outside. Ground crew load 366 passengers. The 747's maximum capacity exceeds 500 in all-economy configuration, but Pan Am operates mixed-class seating. First class occupies the upper deck, the famous hump. Spiral stairs connect upper and lower decks. The configuration includes a lounge area with seating separate from passenger seats, a feature that would disappear in later years as airlines prioritized revenue over ambiance. The main deck carries economy class in 10 abreast configuration. 2 aisles divide the cabin into sections of 3, 4, and 3 seats across. The cabin is pressurized to maintain 8,000-foot cabin altitude while cruising at 41,000 feet. The pressure differential, the difference between cabin pressure and outside air pressure, reaches 9 psi at cruise altitude. The revolutionary design Boeing designed the 747 in response to 1960s requirements for high-capacity, long-range transport. Airlines projected massive growth in air travel. They needed aircraft that could carry more passengers more economically than existing types. The wide-body concept, twin-aisle cabin with sufficient diameter to accommodate containers side by side, allowed efficient cargo operations and passenger capacity impossible in narrow-body aircraft. Boeing chose the distinctive hump configuration for specific reasons. Placing the cockpit above the main deck allowed the entire nose section to open upward for freight loading. The 747 could operate as freighter or convertible passenger freight configuration. The upper deck created space behind the cockpit. Pan Am requested passenger seating there. The iconic spiral stairs and lounge resulted. Engine start sequence. Hayes initiates engine start for number 3, inboard starboard engine. The procedure differs from smaller aircraft. Ignition on. Start valve open. The JT-9D uses bleed air from the auxiliary power unit to spin the turbine for starting. The compressor begins rotating. At specific RPM, fuel flow initiates. The engine lights off. Exhaust gas temperature rises. The turbofan accelerates toward idle. 6,000 revolutions per minute for the low-pressure spool, 10,000 revolutions per minute for the high-pressure spool. But the sound is different from earlier turbojets. Quieter. The high bypass ratio turbofan generates thrust primarily from the large diameter fan at the front, not from jet exhaust. The bypass air that flows around the engine core rather than through it, provides approximately 80% of total thrust. Engines 4, 2, and 1 follow in sequence. 4 JT-9D turbofans now running, generating 174,000 pounds of combined thrust at takeoff power. Pushback and taxi Morrison receives pushback clearance. The 747 cannot push itself back. Its mass, 735,000 pounds at maximum takeoff weight, requires a powerful tug. The pushback tractor positions, connects to the nose gear. The tug driver coordinates with Morrison via intercom. The 747 begins moving backward, turning onto the taxiway. Pushback complete. Morrison starts taxiing under the aircraft's own power. The 747 handles differently than narrow-body jets. The nose wheel sits far ahead of the pilots, over 70 feet from cockpit to nose gear. Turning requires anticipation. The wingtips extend nearly 100 feet on each side. Clearance requires constant attention. Morrison taxis slowly, following ground controller instructions toward the departure runway. Before takeoff. At the runway hold point, Hayes completes the before takeoff checklist. The procedure is lengthy. Every system requires verification. Flaps, 20 degrees. Stabilizer trim, set for takeoff based on weight and center of gravity. Flight controls, full deflection check, ailerons, elevators, rudder. 4 engines, all parameters green. Fuel, 800,000 pounds. Enough for the transatlantic crossing plus required reserves. The 747's fuel system manages 17 tanks throughout the wings and center fuselage. Hayes monitors quantity in each tank, plans fuel transfers during flight to maintain proper center of gravity as fuel burns. Takeoff performance. The 747 requires careful takeoff performance calculation. Weight, temperature, pressure altitude, runway length, wind. All factors affect the speeds and distances. Today's conditions: Heathrow runway 27L, 12,000 feet long. Gross weight, 710,000 pounds. Temperature, 42 degrees Fahrenheit. Light headwind. Calculated speeds. V1 decision speed, 165 knots. Rotation speed, 170 knots. V2 initial climb speed, 185 knots. The 747 will use approximately 9,000 feet of runway for takeoff under these conditions. Takeoff tower clears Flight 002 for takeoff. Morrison advances all 4 throttles to approximately 90% thrust. Hayes monitors engine instruments, confirms all 4 JT-9Ds developing equal power. The 747 begins accelerating. Slowly at first, 710,000 pounds resists movement. But the acceleration builds as airspeed increases. 100 knots, 140 knots. Chen calls speeds. Morrison maintains directional control with rudder and nose wheel steering, keeping the aircraft aligned with centerline. V1. Decision speed. Committed to takeoff. Rotate. Morrison applies gentle back pressure to the control yoke. The nose lifts. The angle of attack increases. The massive wing generates lift. For a moment, the main landing gear still supports full weight. Then the wing's lift exceeds weight. The 747 becomes airborne, climbing at 1,200 feet per minute despite its mass. The climb gear retraction. Chen raises the landing gear handle. The complex mechanism retracts 16 main wheels and 2 nose wheels into wheel wells, closing doors to maintain clean aerodynamics. The 747 climbs westbound over England, following the departure procedure. At 10,000 feet, flaps retract to clean configuration. Airspeed increases toward climb schedule. Hayes monitors engine parameters closely during climb. The JT-9D engines run hot. Exhaust gas temperature requires constant attention. The engines operate near their thermal limits during maximum climb power. At 18,000 feet, the crew switches to standard altimeter setting. All aircraft above this altitude reference the same pressure datum, 29.92 inches of mercury. The 747 continues climbing. 20,000 feet, 30,000 feet. The rate of climb decreases as altitude increases and air density decreases. Cruise altitude. At 41,000 feet, Morrison levels the aircraft. Hayes reduces power to cruise settings. The 4 JT-9Ds settle into efficient cruise operation, burning approximately 15,000 pounds of fuel per hour total. Airspeed. Mach 0.84. Approximately 550 miles per hour true airspeed at this altitude. The 747 cruises faster than most previous generation aircraft, despite its size. The autopilot maintains heading and altitude, but the system is basic compared to later versions. The crew remains actively engaged, monitoring flight path, managing systems, coordinating with air traffic control. The North Atlantic Track. The flight plan follows North Atlantic Track Alpha, one of several daily routes across the ocean. The tracks change daily based on wind patterns, optimizing eastbound and westbound traffic for prevailing winds. Navigation uses a combination of methods. Inertial navigation systems. 3 independent units calculating position based on accelerometers and gyroscopes. VOR navigation when within range of ground stations. Celestial navigation backup using sextant sights through cockpit windows. Radio communication with oceanic control centers occurs at scheduled positions. The crew transmits position reports every hour or at designated waypoints. Systems management in flight. Hayes continuously manages aircraft systems. Fuel transfer between tanks maintains center of gravity within limits as fuel burns. The 747's CG range is critical. Too far aft and the aircraft becomes unstable. Too far forward and elevator authority decreases. He monitors hydraulic systems. 4 independent systems provide redundancy, each powered by different engines. If one system fails, 3 remain. If 2 fail, the aircraft can still operate safely. Electrical generation. 4 engine-driven generators produce AC power. The APU provides backup. Battery power serves as final reserve. Pneumatic systems. Bleed air from engines provides cabin pressurization, air conditioning, and wing anti-ice. Hayes monitors bleed air temperature and pressure, ensuring adequate supply without overheating components. The flight deck experience. Flying the 747 manually requires constant attention. The flight controls are hydraulically powered, but the aircraft's mass creates momentum that pilots must anticipate. Pitch changes take time. The 747 doesn't respond instantly to control inputs like lighter aircraft. Pilots learn to lead the aircraft, applying control before reaching the desired attitude, then neutralizing as the aircraft reaches target pitch or bank. The auto throttle system, not installed on early 747-100s, would arrive in later variants. For now, Morrison and Chen manually adjust throttles to maintain speed, or Hayes manages them while pilots handle flight controls. Mid-Atlantic position. 3 hours into the flight, the 747 crosses the Mid-Atlantic waypoint. Fuel consumption tracking as planned. No system anomalies. Weather at destination acceptable. The cabin crew has completed meal service. Passengers settle into the long crossing. Some sleep, others read or watch the in-flight movie projected onto screens mounted in the cabin. Outside, the temperature reads -60 degrees Celsius. The air pressure equals approximately 2 psi. Humans cannot survive in this environment without pressurization. Inside, the cabin maintains comfortable conditions. Pressurized to 8,000 feet, temperature controlled. Fresh air continuously circulated through the environmental control system. Descent planning. 400 miles from New York, Morrison receives clearance to begin descent from cruise altitude. The descent must be carefully managed. The 747 carries tremendous kinetic energy at cruise, 700,000 pounds moving at Mach 0.84. Converting altitude to distance requires planning and coordination. Morrison begins descent, maintaining descent rate around 2,000 feet per minute. Too rapid and passengers experience discomfort. Too slow and fuel efficiency decreases. Hayes monitors engine parameters during descent. Rapid power reductions can shock cool turbofan engines. He manages power carefully, maintaining adequate thrust while descending. Approach to New York. At 20,000 feet, New York approach control vectors, Flight 002 into the arrival pattern. The crew configures for landing. Flaps extend in stages, 1 degree, 5 degrees, 10 degrees, 20 degrees. Each extension increases drag and reduces stall speed. Landing gear lowers. 16 main wheels and 2 nose wheels deploy, creating significant drag. Airspeed decreases toward final approach speed. The 747's approach speed depends on weight. Today, with fuel burned during the crossing, the aircraft weighs approximately 550,000 pounds. Final approach speed, 150 knots. Landing, runway. 31L at JFK extends 13,400 feet, more than adequate for the 747's landing requirements. Morrison flies the visual approach, following the glide slope toward the threshold. Chen monitors speeds and configuration. Hayes confirms all systems ready for landing. The runway threshold passes beneath. Morrison reduces power, initiating the flare. The 747's landing technique requires precise timing. Flare too early, and the aircraft balloons. Too late, and the landing is firm. The main gear contacts the runway. 16 wheels, simultaneously absorbing the energy of 550,000 pounds, settling onto concrete. Morrison deploys thrust reversers on all 4 engines. The reverser cascades redirect engine exhaust forward, providing deceleration force. Wheel brakes supplement the reversers. The 747 decelerates, slowing to taxi speed within 8,000 feet. Arrival flight, 002 taxis to the gate. Ground crew position jetways to both main deck and upper deck doors. Passengers begin deplaning. Morrison, Chen, and Hayes complete the shutdown checklist. 4JT-9D engines wind down to silence. Hydraulic systems depressurize. Electrical power transfers from engines to ground power. The transatlantic crossing is complete. London to New York in 7 hours, 42 minutes. The 747's impact. The original 747 transformed commercial aviation fundamentally. It proved wide-body transport viable. It demonstrated that very large aircraft could operate economically. It made intercontinental travel accessible to millions who couldn't afford previous ticket prices. The basic design proved so sound that 747 variants continued production for over 50 years. The 747-8, the final version, shared the same fundamental configuration as this 1977 47-100. But the original required skills and procedures now obsolete. 3-person crews, analog systems, manual fuel management, navigation without computers. Evening at JFK, The sun sets over New York as the crew completes their paperwork. Tomorrow, they'll fly the return leg to London. Same aircraft, same procedures, same analog systems requiring constant crew attention. The 747 that made aviation democratic. That shrank the world by making distance routine. That proved wide-body transport could work, not through automation, through engineering that created reliable systems requiring skilled human management. The aircraft that changed everything while requiring crews to fly it with the same fundamental skills pilots had used for decades.